The universe contains black holes spanning an extraordinary range of masses, from stellar remnants weighing just a few times the mass of the Sun to the supermassive behemoths anchoring galactic cores that contain millions or billions of solar masses, and between these two well-established populations lies a theoretically predicted but observationally elusive intermediate category, black holes with masses ranging from roughly 100 to 100,000 times that of the Sun, objects that should exist according to various formation scenarios but have proven remarkably difficult to detect and confirm with certainty, and among the handful of candidate intermediate mass black holes that astronomers have identified over the past 2 decades. Perhaps none has generated more sustained interest and scientific debate than the ultraluminous X-ray source designated M82X1, located within the spectacular starburst galaxy Messier 82, also known as the Cigar Galaxy due to its elongated appearance in visible light images, positioned approximately 12 million light-years distant in the direction of the constellation Ursa Major, where observations across multiple wavelengths reveal a galaxy undergoing an extraordinary episode of star formation. Triggered by gravitational interactions with its larger neighbor Messier 81, producing new stars at a rate roughly 10 times faster than the Milky Way's leisurely pace of 1 to 2 solar masses per year, and within this cauldron of stellar birth and evolution. The X-ray source M82X1 shines with a luminosity that exceeds by factors of hundreds the theoretical maximum that stellar mass black holes can sustain through standard accretion processes, suggesting either that conventional theoretical limits fail under the extreme conditions present in this source or that M82X1 harbors a black hole substantially more massive than those produced by stellar evolution, an intermediate mass black hole containing perhaps several hundred solar masses that represents a missing link between stellar and supermassive black holes, and the evidence supporting this interpretation has accumulated gradually through decades of observations using virtually every major X-ray observatory launched since the 1980s, including Einstein, Rosat, ASCA, Chandra, XMM Newton, NuSTAR, and others, each contributing pieces to the puzzle through measurements of the source's brightness, spectrum, variability, and spatial properties, gradually building a case that M82X1 indeed represents something genuinely unusual and potentially transformative for our understanding of how black holes form and grow across cosmic time, though alternative explanations remain possible and continue to be debated among researchers who study the complex physics of accretion under extreme conditions where radiation pressure, magnetic fields, and geometric effects can conspire to produce luminosities exceeding the classical theoretical limits that apply to simplified models of spherically symmetric steady-state accretion. And the resolution of this debate carries implications extending far beyond the specific case of M82X1 to encompass fundamental questions about the formation mechanisms that produce black holes across the full mass spectrum, the efficiency and geometry of accretion flows operating near or above the Eddington limit where radiation pressure becomes comparable to or exceeds gravitational attraction, the role of intermediate mass black holes as potential seeds for the supermassive black holes observed in distant quasars when the universe was less than 1 billion years old, and the demographics of compact objects in dense stellar environments where dynamical interactions and stellar collisions might produce exotic outcomes impossible in the more sedate stellar populations characteristic of the solar neighborhood. The host galaxy Messier 82 has captivated astronomers since its discovery by Johann Alert Bode in December 1774. Though its true nature as an external galaxy rather than a nebula within the Milky Way remained unclear until the 1920s when Edwin Hubble's observations of Cepheid variable stars in other galaxies established the extragalactic distance scale and revealed that the universe extends far beyond our own stellar system, and subsequent observations of M82 showed it to be a galaxy of irregular morphology with a mass of perhaps 30 to 40 billion solar masses. Substantially smaller than giant spirals like the Milky Way or Andromeda but still containing hundreds of millions of stars along with vast quantities of gas and dust concentrated particularly in the central regions where the starburst activity reaches its peak intensity, and this burst of star formation, which began approximately 10 to 15 million years ago following a close gravitational encounter with the much larger spiral galaxy M81 located approximately 300,000 light years away, has transformed the galactic core into a factory producing massive stars at a prodigious rate, and these massive stars, with lifetimes of only millions of years compared to billions of years for Sun-like stars, rapidly exhaust their nuclear fuel and explode as supernovae. releasing enormous quantities of energy and heavy elements into the surrounding interstellar medium and creating expanding bubbles of hot gas that eventually break through the galactic disk and drive powerful outflows extending thousands of light-years perpendicular to the plane, visible in optical images as reddish filaments of ionized hydrogen tracing the paths of this galactic superwind. And the combination of intense star formation, frequent supernova explosions, and vigorous outflows makes M82 one of the nearest and most thoroughly studied examples of starburst galaxy activity, a phenomenon that was far more common in the early universe when galaxies formed and merged more frequently and when the available gas supply had not yet been depleted by billions of years of star formation. And understanding the physics of starbursts provides crucial insights into galaxy evolution across cosmic time, including the mechanisms that regulate star formation, the production and dispersal of heavy elements essential for planet formation and potentially for life, and the feedback processes through which star formation and black hole growth influence their environments and ultimately limit their own activity by heating or expelling the gas reservoirs they require, and the gravitational interaction between M82 and M81 that triggered the current starburst represents a relatively mild example of the tidal encounters that can occur between galaxies, producing distortions in the stellar distributions and driving gas inflows toward the galactic centers where enhanced densities trigger bursts of star formation, and astronomers have mapped the neutral hydrogen gas distribution in the M81 group using radio telescopes, revealing tidal bridges and streams of material connecting the galaxies and documenting the ongoing exchange of matter facilitated by their gravitational dance, and theoretical models of the encounter history combining n-body simulations that track the motions of millions of test particles representing stars and dark matter with hydrodynamical calculations that follow the behavior of the gaseous component have reconstructed the likely trajectory of M82 relative to M81 over the past several hundred million years, showing multiple close passages that have progressively disrupted M82's structure and triggered successive episodes of enhanced star formation, with the current starburst representing perhaps the most intense phase of this activity. Within this tumultuous environment of rapid stellar birth and death, M82 harbors numerous intense X-ray sources that mark the locations of compact objects, neutron stars, and black holes that have formed from the deaths of massive stars and that now accrete material from companion stars or from the surrounding interstellar medium, and among these X-ray sources M82X. One stands out not only for its exceptional brightness but also for its persistence, remaining active across decades of observations. While other ultraluminous X-ray sources in M82 and other galaxies have shown dramatic variability or disappeared entirely, and the source lies embedded within a superstar cluster, a dense aggregation of young stars with a total mass estimated at several tens of thousands of solar masses concentrated within a region measuring just a few light-years across, comparable in mass to globular clusters but far younger, with ages of only 10 to 20 million years compared to the 10 billion-year ages typical of globular clusters orbiting the Milky Way, and these superstar clusters form during intense starbursts when giant molecular clouds containing millions of solar masses of gas collapse gravitationally and fragment into thousands of individual stars over timescales of just a few million years, and the proximity of M82X1 to such a massive young stellar system provides important clues about its formation mechanism, suggesting that the black hole may have formed within the cluster itself either through the direct collapse of an exceptionally massive star with an initial mass exceeding 100 or even several hundred solar masses, far above the typical upper limit of stellar masses in most star-forming regions but potentially achievable in the extreme conditions of superstar clusters where stellar collisions and mergers might build up such massive objects, or through the successive mergers of stellar mass black holes within the dense stellar environment where dynamical interactions occur frequently and can lead to black hole binaries that eventually coalesce through gravitational wave emission, gradually building up the mass of the resulting black hole through multiple merger episodes spanning millions of years, and distinguishing between these formation scenarios represents one of the key questions driving ongoing research into intermediate mass black holes, with important implications not only for understanding M82X1 specifically but more broadly for determining whether intermediate mass black holes represent a common phase in black hole evolution and whether they might serve as seeds for the supermassive black holes that eventually grow to dominate galactic nuclei, and the stellar population within the superstar cluster hosting M82X1 shows spectroscopic signatures indicating ages of approximately 15 million years. placing the cluster formation roughly contemporaneous with the onset of the most recent starburst episode, and the cluster contains numerous Wolf-Rayet stars, highly evolved massive stars that have shed their hydrogen envelopes through strong stellar winds and now display spectra dominated by emission lines from helium, carbon, nitrogen, and oxygen synthesized through nuclear fusion in their interiors. And these Wolf-Rayet stars represent late evolutionary stages of stars with initial masses exceeding 25 solar masses, and their presence confirms the cluster's youth and demonstrates that substantial numbers of very massive stars formed during the initial starburst, providing both the raw material for black hole formation through direct collapse and the dynamical environment necessary for black hole mergers if the hierarchical formation scenario operates, and the total number of Wolf-Rayet stars observed in the cluster, approximately 20 to 30 based on spectroscopic surveys, implies an initial population of massive stars numbering in the hundreds or thousands, of which perhaps 10 to 20% have already evolved through their complete life cycles and exploded as supernovae, leaving behind neutron stars or stellar mass black holes, and this population of compact remnants provides the reservoir from which an intermediate mass black hole could potentially grow through successive mergers if the cluster dynamics favor such hierarchical growth. The X-ray emission from M82X1 originates from an accretion flow surrounding the central black hole, where material drawn from a companion star or captured from the surrounding medium spirals inward while converting gravitational potential energy into thermal energy and ultimately into electromagnetic radiation that escapes to reach distant observers, and the fundamental physics of this accretion process follows principles similar to those operating in other black hole systems, with differential rotation generating viscosity that transports angular momentum outward while allowing mass to flow inward, and with the gravitational energy released by the infalling material heating the accretion flow to temperatures of millions of degrees where thermal emission peaks in the X-ray portion of the spectrum, but the extreme luminosity of M82X1, which reaches approximately 10 to the 40 ergs per second or roughly 100 million times the total power output of the Sun across all wavelengths, creates conditions where radiation pressure becomes a dominant force competing against gravity and potentially modifying the structure and dynamics of the accretion flow in fundamental ways, and to understand why this luminosity is so remarkable requires considering the Eddington limit. A fundamental theoretical constraint first derived by Arthur Eddington in the 1920s for understanding stellar structure but equally applicable to accreting black holes, which states that for a spherically symmetric system in hydrostatic equilibrium the maximum sustainable luminosity occurs when the outward radiation pressure force on electrons exactly balances the inward gravitational attraction, and for a black hole of a given mass this critical luminosity scales directly with the mass equaling approximately 1.3 times 10 to the 38 ergs per second per solar mass of the black hole, or equivalently about 30,000 times the solar luminosity per solar mass. So that a 10 solar mass black hole can sustain at most 300,000 solar luminosities or approximately 4 times 10 to the 38 ergs per second, while a million solar mass black hole could reach 3 times 10 to the 44 ergs per second, and the significance of this relationship becomes clear when we calculate the Eddington luminosity for different assumed masses of M82X1, finding that if the source contains only a stellar mass black hole of 10 to 20 solar masses, then its observed luminosity of approximately 10 to the 40 ergs per second exceeds the Eddington limit by factors of 5 to 10, seemingly violating the fundamental constraint that radiation pressure should blow away the accreting material and halt the accretion process. While if the black hole contains several hundred solar masses placing it firmly in the intermediate mass category, then the observed luminosity remains comfortably below the Eddington limit at perhaps 20 to 40% of the critical value and poses no theoretical difficulty, and this comparison provides one of the primary arguments supporting the intermediate mass interpretation of M82X1, though researchers have identified several mechanisms that might allow stellar mass black holes to exceed their Eddington luminosities at least temporarily, including geometric effects where the emission emerges preferentially in narrow beams rather than isotropically, reducing the radiation pressure experienced by the inflowing material even while producing high apparent luminosities for observers lying within the beam, a phenomenon known as super-Eddington beaming that has been invoked to explain some ultraluminous X-ray sources or situations where the accretion flow becomes geometrically thick and optically thin, allowing radiation to escape more easily without exerting as much pressure on the surrounding material, creating configurations sometimes called Advection-dominated accretion flows where a substantial fraction of the gravitational energy is advected into the black hole rather than being radiated, though this scenario seems less applicable to bright sources like M82X1 where the high luminosity indicates efficient radiation. Or configurations where strong magnetic fields channel the flow and modify the effective radiation pressure, potentially allowing material to accrete along magnetic field lines even when the luminosity exceeds the spherical Eddington limit. And evaluating these alternatives requires detailed analysis of the observed spectral and temporal properties to look for signatures that might distinguish between different geometric configurations and accretion regimes, and the weight of evidence increasingly favors the intermediate mass black hole interpretation as more straightforward and requiring fewer special geometric assumptions than the alternatives, though definitive proof remains elusive given the inherent ambiguities in interpreting electromagnetic observations of distant compact objects. The X-ray spectrum of M82X1 shows distinctive features that provide important diagnostics for understanding the physical conditions in the accretion flow and the nature of the central compact object. And observations using the Chandra X-ray Observatory with its excellent spatial resolution allowing the source to be cleanly separated from other nearby X-ray sources in the crowded central regions of M82 and XMM Newton with its larger collecting area providing superior sensitivity for detailed spectroscopy, and New Star with its unique capability to observe hard X-rays at energies above 10 keV where most other missions have limited or no sensitivity, have collectively revealed a complex spectral shape that can be approximated by a combination of multiple components, including a soft thermal component with a characteristic temperature of approximately 1 to 200 electron volts corresponding to emission from the outer regions of an accretion disk where temperatures remain relatively cool and the thermal radiation peaks in the soft X-ray and ultraviolet portions of the spectrum, plus a harder power law component extending to high energies and likely arising from Compton scattering processes where soft photons from the disk gain energy through collisions with hot electrons in a corona surrounding the disk, and careful analysis of these spectral components and how they vary with time provides clues about the geometry and physical conditions in different regions of the accretion flow, with the temperature and luminosity of the disk component depending on the mass accretion rate and the inner radius where the disk is truncated either by the innermost stable circular orbit around the black hole or by other effects such as magnetic pressure or radiation pressure that might disrupt the disk structure in the innermost regions, and the photon index characterizing the slope of the power law component reflecting the temperature and optical depth of the Comptonizing region, and multiple research groups have fitted sophisticated models to the observed spectra attempting to constrain these parameters and thereby infer properties of the black hole and its environment. And while the details vary somewhat depending on the specific models employed and the particular observations analyzed, a general consensus has emerged that the spectral properties are consistent with accretion onto a black hole with mass in the range of a few hundred to perhaps 1,000 solar masses, substantially above the stellar mass range but well below the supermassive category, though the uncertainties in these mass estimates remain substantial, typically factors of 2 or 3, due to the model dependencies and the limited constraining power of the available data, and future observations with improved spectral resolution and broader energy coverage could help narrow these uncertainties and provide more definitive mass constraints. And one particularly diagnostic spectral feature that astronomers have searched for is the characteristic thermal emission from the inner accretion disk, which according to standard thin disk theory should peak at a temperature determined by the black hole mass, the mass accretion rate, and the inner disk radius, with the relationship following from balancing the viscous energy dissipation rate against the local radiative cooling, and for intermediate mass black holes accreting at substantial fractions of their Eddington rates this peak temperature should fall in the soft X-ray to extreme ultraviolet range, making it potentially observable with current X-ray observatories. And several studies have claimed to detect this thermal disk component in M82X1 with temperatures of approximately 100 to 200 electron volts, consistent with expectations for a several hundred solar mass black hole, though other researchers have questioned whether the observed soft component truly represents direct disk emission or whether it might arise from reprocessing of harder X-rays in surrounding material or from other emission processes, and resolving this ambiguity would benefit from simultaneous observations spanning from optical wavelengths through soft X-rays to hard X-rays, capturing the full spectral energy distribution and allowing more robust modeling that could definitively identify the various emission components and their physical origins. The temporal variability exhibited by M82X1 offers another window into the physics of the accretion flow and provides additional evidence regarding the mass of the central black hole, and detailed timing analysis of long observations with XM Newton has revealed quasi-periodic oscillations in the X-ray brightness, regular modulations occurring with a characteristic timescale of approximately 62 days that repeat over multiple cycles with remarkable consistency, a periodicity first reported in 2014 by researchers analyzing archival data spanning more than a decade and subsequently confirmed through additional observations extending the temporal baseline and improving the statistical significance of the detection. And the physical origin of this periodicity has been the subject of considerable debate, with proposed explanations including orbital motion of a companion star supplying material to the black hole, where the 62-day period would correspond to the binary orbital period, or precession of the inner accretion disk due to relativistic effects in the strong gravitational field near the black hole, where the disk axis traces out a cone over the course of the precession cycle and the resulting changes in viewing geometry produce modulations in the observed X-ray flux, or oscillations in the structure of the accretion flow itself driven by radiation pressure instabilities or magnetic field effects that establish characteristic timescales related to the dynamical or thermal timescales of the flow. And distinguishing between these scenarios requires examining how the periodic signal manifests across different energy bands and whether there are accompanying changes in the spectral properties or in the character of shorter timescale variability. And the precession interpretation has gained support from detailed modeling showing that for a black hole mass of several hundred solar masses accreting at close to its Eddington rate, relativistic frame dragging effects should indeed produce precession of a tilted accretion disk with a period roughly consistent with the observed 62-day modulation, and this interpretation provides independent support for the intermediate mass hypothesis. As stellar mass black holes would produce much shorter precession periods of hours to days rather than months, while the observed period naturally emerges for black holes in the several hundred solar mass range, though alternative explanations remain viable and additional observations tracking the evolution of the periodic signal over many cycles and examining correlations with spectral changes would help further constrain the physical mechanism, and the precession of accretion disks represents a well-established phenomenon in general relativistic astrophysics, arising from the Lenz-Thirring effect where the rotation of the central black hole drags spacetime along with it and exerts torques on any tilted disk, forcing the disk angular momentum vector to precess around the black hole's spin axis. And the precession period depends on the black hole mass, its spin rate, and the radial extent of the disk, with typical scaling suggesting that the precession period should be proportional to the black hole mass for otherwise similar systems, and applying these scaling relationships to the observed 62-day period in M82X. One yields black hole mass estimates in the range of 400 to 800 solar masses depending on assumptions about the black hole spin and disk geometry broadly consistent with the mass estimates derived from spectral modeling and providing independent confirmation through a completely different physical mechanism. Beyond the 62-day quasi-periodic oscillation, M82X1 exhibits variability on a wide range of other timescales, including irregular fluctuations on timescales of hours to days likely associated with turbulent variations in the accretion rate or with instabilities in the accretion flow structure, and occasional larger amplitude changes over weeks to months where the source brightness can vary by factors of 2 or more, possibly reflecting more substantial reorganizations of the accretion geometry or changes in the mass supply rate from the companion star or surrounding medium, and at the shortest timescales accessible with current X-ray detectors, down to intervals of seconds or less. The source shows complex stochastic variability with statistical properties that can be characterized through power spectral analysis, revealing how the variance in brightness is distributed across different temporal frequencies, and this power spectrum provides fingerprints of the physical processes operating in the accretion flow with the overall shape and characteristic timescales depending on the black hole mass, the accretion rate, and the geometry of the emitting regions, and comparisons between the observed power spectrum of M82X1 and those measured for well-characterized stellar mass black holes in the Milky Way show both similarities and differences. With the general shape of the power spectrum showing a similar broadband noise component but with characteristic timescales that appear stretched to longer values by roughly the factor expected if M82X1 contains a black hole several hundred times more massive than typical galactic black hole binaries, since many timescales in accretion flows scale approximately with the black hole mass. reflecting the longer dynamical times associated with orbits at larger radii for more massive central objects, and this scaling relationship provides yet another independent line of evidence supporting the intermediate mass interpretation. Though again with substantial uncertainties due to the complexity of accretion flow physics and a limited theoretical understanding of how power spectra should depend on all the relevant parameters including not just black hole mass but also accretion rate, magnetic field strength, and geometric configuration, and detailed studies of stellar mass black hole systems in the Milky Way have established empirical relationships between observed variability properties and black hole masses, showing that characteristic frequencies in the power spectra scale inversely with mass, and extrapolating these relationships to the variability properties observed in M82X, one yields mass estimates again in the several hundred solar mass range, providing yet another confirmation through independent methodology. And the consistency among mass estimates derived from multiple different techniques, including spectral modeling of the thermal disk component, analysis of the 62-day quasi-periodic oscillation, and power spectral analysis of the rapid variability, substantially strengthens the case for the intermediate mass interpretation since each method involves different physical assumptions and systematic uncertainties, and the convergence towards similar mass estimates despite these differences suggests that the conclusions are robust rather than artifacts of any single analysis approach. The search for intermediate mass black holes extends far beyond M82X1 to encompass observations of ultraluminous X-ray sources throughout the local universe, a heterogeneous population of bright X-ray sources found primarily in star-forming galaxies where young stellar populations provide both potential progenitors for intermediate mass black holes and abundant sources of material for accretion. And systematic surveys using Chandra and M82 have identified several hundred ultraluminous X-ray sources with luminosities exceeding 10 to the 39 ergs per second, the nominal Eddington limit for a 10 solar mass black hole, and for the brightest of these sources with luminosities reaching 10 to the 40 ergs per second or higher, similar to M82X1. The evidence increasingly suggests that at least some fraction must contain intermediate mass black holes rather than stellar mass objects accreting at super-Eddington rates, though determining which specific sources fall into which category remains challenging and requires detailed analysis of individual objects combining spectroscopic, timing, and spatial information, and some sources previously considered strong intermediate mass black hole candidates have been reclassified following the discovery that they contain neutron stars rather than black holes, identified through the detection of coherent pulsations with periods of seconds that can only arise from rotating magnetized neutron stars channeling accretion flow onto their magnetic poles. And these neutron star ultraluminous X-ray sources demonstrate conclusively that at least some compact objects can sustain luminosities well above their Eddington limits, presumably through a combination of geometric beaming effects and the influence of strong magnetic fields that can reach trillions of times Earth's surface field strength. And the recognition that neutron stars can masquerade as intermediate mass black holes has complicated the interpretation of ultraluminous X-ray sources and injected healthy skepticism into claims of intermediate mass black hole detections, requiring more stringent tests and multiple independent lines of evidence before any source can be confidently classified as harboring an intermediate mass black hole. And in this context M82X1 remains among the most compelling cases due to the convergence of multiple arguments including its exceptional luminosity, its location within a massive star cluster providing a plausible formation environment, its spectral properties consistent with accretion onto a several hundred solar mass black hole, its 62-day quasi-periodic oscillation matching expectations for disk precession around an intermediate mass black hole, and its long-term stability over decades of observations suggesting a massive central object rather than a temporary super-Eddington phase that might characterize stellar mass systems undergoing transient outbursts. And importantly, no coherent pulsations have been detected from M82X1 despite deep searches in high-time resolution data from multiple observations, which would definitively identify a neutron star if present, and while the absence of detected pulsations does not prove the absence of a neutron star since various geometric or physical effects could potentially obscure pulsations, it at least keeps the black hole interpretation viable and eliminates one of the simplest alternative explanations for the exceptional luminosity. The theoretical understanding of how intermediate-mass black holes might form remains incomplete despite decades of research exploring various possibilities, and the difficulty lies partly in identifying formation channels that can produce objects in this mass range while avoiding the complications that prevent straightforward extrapolation from either stellar mass black holes formed through the collapse of massive stars or supermassive black holes growing through accretion and mergers in galactic nuclei, and stellar evolution theory suggests that stars with initial masses exceeding roughly 25 solar masses should collapse to form black holes rather than exploding as supernovae. With the mass of the resulting black hole typically ranging from several solar masses up to perhaps 50 or at most 100 solar masses for the most massive stellar progenitors, but reaching the several hundred solar mass range required to explain M82X, one through this direct collapse channel would require progenitor stars with initial masses of several hundred solar masses or more, and such extremely massive stars likely existed in the early universe when the composition of star-forming gas consisted almost entirely of hydrogen and helium without the heavier elements that contribute to stellar winds capable of stripping away the outer envelope and limiting the final mass. But in the present-day universe with gas enriched by billions of years of stellar nucleosynthesis and supernova explosions, the formation of such massive stars appears highly unlikely except perhaps in the most extreme environments, though the extreme conditions in superstar clusters might potentially enable unusual formation modes including collisional runaway processes where repeated mergers between stars and the dense cluster core build up an exceptionally massive object before it has time to evolve and explode, and numerical simulations of superstar cluster evolution have explored this possibility, showing that under favorable conditions a very massive star could potentially form through this runaway process and subsequently collapse to produce an intermediate mass black hole. Though the parameter space where this works successfully appears quite limited and many simulations show that the massive merger product tends to explode rather than collapse, dispersing its mass rather than creating a black hole, and the success of this channel depends sensitively on the cluster density, the initial mass function governing the distribution of stellar masses at birth, the efficiency of mass loss through stellar winds, and the uncertain physics governing the stability and evolution of very massive stars, and alternative formation channels involving the successive merger of stellar mass black holes within dense clusters offer another possibility, where dynamical interactions in the cluster core lead to the formation of black hole binaries that merge through gravitational wave emission, and the merger product can be retained in the cluster despite receiving a velocity kick from anisotropic gravitational wave emission if the cluster's escape velocity is sufficiently large, and this black hole can then participate in subsequent encounters and mergers, gradually building up its mass through multiple merger episodes spanning millions of years. And detailed cluster dynamic simulations including the effects of stellar evolution, binary interactions, and gravitational wave emission have shown that this hierarchical merger scenario can plausibly produce intermediate mass black holes with masses reaching several hundred solar masses within the 10 to 20 million year ages characteristic of superstar clusters observed in starburst galaxies, and the merger rates and mass distributions predicted by these simulations broadly match the inferred properties of ultraluminous X-ray sources like M82X1, though significant uncertainties remain in the treatment of various physical processes including the retention fraction of merger products which depends on the natal kicks imparted during black hole formation and during binary mergers. The efficiency of black hole binary formation in dense stellar environments where three-body interactions can both create and destroy binaries, and the importance of gas dynamical effects that might enhance accretion rates and facilitate black hole growth beyond what merger processes alone can achieve, and recent advances in numerical techniques including the development of sophisticated n-body codes capable of tracking millions of stars including binary interactions and stellar evolution, and direct integration of post-Newtonian equations of motion to accurately model the orbital evolution and merger of black hole binaries including gravitational wave emission, have enabled increasingly realistic simulations that can test these formation scenarios and make detailed predictions for comparison with observations. The broader astrophysical significance of intermediate mass black holes extends well beyond their intrinsic interest as unusual objects occupying a previously unobserved mass range, as these objects likely play important roles in several key processes that have shaped the evolution of galaxies throughout cosmic history, including potentially serving as seeds for supermassive black hole formation in the early universe. since the supermassive black holes observed in quasars at redshifts beyond 6, corresponding to times when the universe was less than 1 billion years old, contain masses approaching billions of solar masses yet had only a limited time available for growth, requiring either extremely efficient accretion at the maximum Eddington rate sustained over most of cosmic history or alternatively starting from more massive seed black holes in the intermediate mass range that could then reach supermassive scales through more moderate growth, and the question of whether supermassive black holes grew from stellar mass seeds of 10 to 100 solar masses or intermediate mass seeds of 1,000 to 100,000 solar masses remains one of the outstanding problems in understanding the formation and evolution of galaxies, with different seed scenarios predicting different populations of intermediate mass black holes in the present-day universe. And observations of ultraluminous X-ray sources like M82 provide crucial constraints on these models by revealing whether intermediate mass black holes exist in significant numbers in star-forming environments and by characterizing their properties and demographics, and theoretical models exploring the light seed scenario where supermassive black holes grow from stellar mass progenitors must invoke sustained super-Eddington accretion or unusually high duty cycles where the black holes spend most of their time actively accreting, assumptions that strain plausibility given observational constraints on active galactic nucleus demographics and lifetimes. Whereas heavy seed models starting from intermediate mass black holes can reach the observed supermassive black hole masses with more conservative assumptions about accretion efficiency and duty cycles, making them potentially more attractive if intermediate mass black holes indeed form readily through mechanisms operating in the early universe, and the formation mechanisms proposed for intermediate mass black holes in present-day superstar clusters including both direct collapse of very massive stars and hierarchical mergers of stellar mass black holes have analogues in the early universe where the first generation of stars formed from primordial gas likely included some exceptionally massive objects, and where dynamical processes in the dense stellar systems surrounding the first black holes could have driven merger chains leading to rapid mass growth, and confirming that intermediate mass black holes form readily through these mechanisms in nearby galaxies would lend credibility to similar processes operating at high redshift and thereby support the heavy seed formation scenario for supermassive black holes. Beyond their role as potential supermassive black hole seeds, intermediate mass black holes also contribute to the gravitational wave signals that are increasingly being detected by the Laser Interferometer Gravitational Wave Observatory and its international partners including Virgo in Italy and Kagra in Japan, collectively forming a network of ground-based gravitational wave detectors that have revolutionized astronomy since their first detection of merging black holes in September 2015 and mergers between intermediate mass black holes or between intermediate mass and stellar mass black holes should produce gravitational wave bursts at frequencies of approximately 10 to 100 Hz where current detectors have good sensitivity, with the characteristic frequency of the gravitational wave signal scaling inversely with the total mass of the merging system, so that stellar mass black hole mergers produce signals peaking near 100 Hz while supermassive black hole mergers occur at much lower frequencies accessible only to space-based detectors or pulsar timing arrays, and intermediate mass black hole mergers occupy the sweet spot for ground-based detectors, potentially producing the loudest signals detectable from across the observable universe, and several candidate events detected during recent observing runs have been interpreted as possible mergers involving intermediate mass black holes based on the inferred masses of the merging objects exceeding 100 solar masses for the heavier component. Though confirming these interpretations and distinguishing definitive intermediate mass black hole mergers from the high-mass tail of the stellar mass black hole population remains challenging given measurement uncertainties, and as the detector network continues to operate and undergo successive upgrades improving sensitivity and expanding the accessible volume of the universe, the rate of intermediate mass black hole merger detections should increase, allowing statistical studies of this population including measurements of the merger rate density as a function of redshift, the mass distribution of merging intermediate mass black holes, and the spin distribution which carries information about formation mechanisms and prior merger history. And the comparison between gravitational wave detections revealing the population of merging intermediate mass black holes throughout the universe and X-ray observations of actively accreting systems like M82 will provide complementary perspectives on this population, probing both the demographics of isolated intermediate mass black holes that occasionally merge through dynamical encounters or binary evolution and those that reside in gas-rich environments where they can accrete and produce Electromagnetic signatures, and this multi-wavelength and multi-messenger approach combining information from different types of observations promises to yield a comprehensive understanding of intermediate mass black holes that has eluded astronomers working with electromagnetic observations alone. And the synergy between gravitational wave and electromagnetic observations extends beyond simple demographics to include the possibility of identifying electromagnetic counterparts to gravitational wave events, where the merger of intermediate mass black holes and gas-rich environments might produce observable signatures including prompt emission from shocked and heated gas, longer-term emission from accretion of material falling back onto the merger remnant or signatures from jets launched by the newly formed black hole, and detecting such counterparts would provide invaluable additional information including precise localization enabling detailed study of the host environment, redshift measurements that are difficult to obtain from gravitational wave observations alone, and insights into the astrophysical context surrounding intermediate mass black hole mergers. The super-star cluster hosting M82X one itself provides a fascinating laboratory for studying stellar dynamics and evolution under extreme conditions, as the combination of high stellar density, with thousands of stars packed into a volume measuring just a few light-years across corresponding to stellar densities exceeding 10,000 stars per cubic parsec compared to roughly 1 star per 10 cubic parsecs in the solar neighborhood, and young age, with most stars having formed within the past 10 to 20 million years, creates an environment quite unlike anything found in the present-day Milky Way, though perhaps resembling conditions in globular clusters during their youth billions of years ago. And within this dense stellar system collisions between stars occur at rates millions of times higher than in the solar neighborhood, with collision timescales of millions of years compared to timescales exceeding the age of the universe for typical field stars, and these collisions can produce exotic objects including blue stragglers that appear younger and more massive than the cluster age would suggest, formed through the merger of lower-mass stars that transfers fresh hydrogen fuel into the stellar core and extends the main sequence lifetime, and exotic binary systems where one star overfills its Roche lobe and transfers mass onto a companion that may be either a normal star or a compact remnant, creating X-ray binaries where accretion onto neutron stars or black holes produces the observed X-ray emission and possibly the intermediate mass black hole powering M82X, one itself through one of the formation mechanisms discussed previously, and observations of this cluster across multiple wavelengths reveal ongoing stellar evolution with numerous Wolf-Rayet stars identified through their distinctive emission line spectra, and these Wolf-Rayet stars represent late evolutionary stages of stars, with initial masses exceeding 25 solar masses that have shed their outer hydrogen envelopes through strong stellar winds driven by radiation pressure on spectral lines. And calculations of stellar evolution for stars in this mass range indicate that Wolf-Rayet phases last only a few 100,000 years before the star explodes as a supernova, so the presence of 20 to 30 Wolf-Rayet stars in the cluster implies a production rate of approximately 1 supernova per 10,000 years, and over the 15 million year lifetime of the cluster this implies that perhaps 1,000 to 1,500 supernovae have already occurred, each releasing approximately 10 to the 51 ergs of energy, roughly equivalent to the Sun's total luminosity integrated over its entire 10 billion year main sequence lifetime, and this enormous cumulative energy input heats and pressurizes the gas within the cluster, potentially driving outflows that remove residual gas and terminate further star formation, and the cluster mass budget must account for substantial mass lost through stellar winds from the massive star population, with estimates suggesting that stellar winds from Wolf-Rayet and other massive stars collectively eject several solar masses per year of processed material enriched in helium, carbon, nitrogen, and oxygen, and through supernovae that collectively have ejected perhaps 10,000 solar masses or more over the cluster's lifetime, representing 10 to 20% of the cluster's initial mass, and the remaining gas within the cluster provides ongoing fuel for accretion onto compact objects including M82X, 1. Supplied either through stellar winds from massive companions if M82X, 1 is part of a binary system, as suggested by the 62-day periodicity if interpreted as an orbital period, or through Bondi-Hoyle accretion from the diffuse intracluster medium if the black hole is effectively isolated, and the mass accretion rate required to sustain the observed luminosity of 10 to the 40 ergs per second can be estimated assuming a radiative efficiency of 10% characteristic of thin disk Accretion onto a non-rotating black hole, yielding a required accretion rate of approximately 10 to the minus 6 solar masses per year, or roughly 3 times 10 to the 20 grams per second. And this accretion rate could plausibly be supplied by the winds from a single massive companion star if M82X1 is in a binary, since Wolf-Rayet stars lose mass at rates of 10 to the minus 5 to 10 to the minus 4 solar masses per year through their intense stellar winds, and even capturing a small fraction of this wind through gravitational focusing would suffice to power the observed emission, or through Bondi-Hoyle accretion if the ambient gas density in the cluster core remains sufficiently high despite the supernova heating and outflows. The observational study of M82X1 has benefited enormously from the relative proximity of the host galaxy at a distance of just 12 million light-years, making M82 one of the nearest starburst galaxies and allowing detailed observations across the electromagnetic spectrum with spatial resolution sufficient to resolve individual star clusters and to separate M82X1 cleanly from other X-ray sources in the galactic center, a capability particularly important given the crowded X-ray source population in M82, where dozens of ultraluminous X-ray sources and hundreds of fainter sources populate the central regions within the 1 kiloparsec radius starburst core, and only the excellent angular resolution of the Chandra X-ray Observatory. Achieving spatial resolution better than 1 arc-second corresponding to roughly 50 light-years at the distance of M82, allows these sources to be studied individually rather than blending together into an unresolved emission complex, and complementary observations using optical and infrared telescopes including the Hubble Space Telescope with its Wide-Field Camera 3 and Advanced Camera for surveys have characterized the stellar populations associated with the X-ray sources, revealing their locations within super-star clusters through direct imaging that resolves the clusters as extended sources with measured half-light radii of 1 to 2 parsecs and total luminosities indicating cluster masses of tens of thousands of solar masses. And spectroscopic observations using both ground-based facilities including the Keck Observatory and the Very Large Telescope and space-based instruments have measured the cluster ages through analysis of the stellar absorption and emission line strengths, with strong hydrogen-Balmer absorption lines indicating ages of several million years when A-type stars dominate the integrated light, and the presence of helium and nitrogen emission lines characteristic of Wolf-Rayet stars confirming ages of 10 to 20 million years when sufficient numbers of massive stars have evolved through their main sequence phases. And these age estimates place important constraints on possible formation mechanisms for M82X1 since any scenario must explain how an intermediate mass black hole could form and begin accreting within the cluster lifetime, and radio observations using the Very Large Array operating at frequencies of 1 to 10 GHz have detected faint radio emission from the position of M82X1 with flux densities of approximately 100 microjanskis, and this radio emission likely arises from synchrotron radiation produced by relativistic electrons spiraling in magnetic fields, and could potentially be associated with jets launched from the vicinity of the black hole as commonly observed in accreting black holes across the mass spectrum from stellar mass systems to supermassive black holes in active galactic nuclei, though the radio emission remains relatively weak compared to some other ultraluminous X-ray sources where strong jets have been clearly identified, and the ratio of radio to X-ray emission in M82X1 falls in the range characteristic of radiatively efficient accretion states where most of the accretion power emerges as electromagnetic radiation rather than being channeled into mechanical energy carried by jets, consistent with the interpretation that M82X1 is accreting at a substantial fraction of its Eddington rate. An ultraviolet spectroscopy using the Cosmic Origin spectrograph aboard Hubble has probed the ionization structure of the gas surrounding M82X1, detecting absorption and emission lines from highly ionized species including O6, Nv, and C4 that indicate the presence of gas heated to hundreds of thousands of degrees by photoionization from the intense X-ray and ultraviolet radiation field produced by the accreting black hole, and mapping the spatial distribution of this ionized gas reveals an extended photoionization nebula surrounding the X-ray source and provides additional constraints on the luminosity and spectral energy distribution of the central engine. The debate surrounding the interpretation of M82X1 1 and other ultraluminous X-ray sources illustrates the healthy scientific process through which the astronomical community evaluates extraordinary claims and gradually converges toward consensus views as evidence accumulates, and the history of this debate spans more than 2 decades, beginning with the first Chandra observations of M82 in 1999 that revealed the exceptional luminosity of X1 with measured 03-10 keV luminosity exceeding 1 times 10 to the 40 ergs per second, and prompted immediate speculation about an intermediate mass black hole given that this luminosity exceeded the Eddington limit for stellar mass black holes by factors of 5 or more. Followed by years of detailed multi-wavelength observations and theoretical modeling that have alternately strengthened and challenged this interpretation as new data emerged and as theoretical understanding of super-Eddington accretion and beamed emission improved, and key turning points in this debate have included the discovery of the 62-day quasi-periodic oscillation announced in 2014 based on analysis of M82 archival data spanning 2004 through 2010, which provided strong new evidence for the intermediate mass interpretation since the observed period matched theoretical expectations for length-stirring precession of an accretion disk around a several hundred solar mass black hole. And the subsequent discoveries starting in 2014 of pulsating ultraluminous X-ray sources where coherent pulsations with periods of seconds definitively identified neutron stars rather than black holes as the central compact objects, which demonstrated that exceptional luminosities alone cannot definitively identify intermediate mass black holes and which injected appropriate caution into the interpretation of ultraluminous X-ray source populations, and the recognition that M82X1 has not shown the coherent pulsations that would unambiguously identify a neutron star despite deep searches in timing data from multiple long observations including dedicated monitoring campaigns specifically targeting potential pulsation signals. Which by itself does not prove the absence of a neutron star since pulsations could potentially be obscured by geometric effects where the beam does not sweep across our line of sight or by irregularities in the accretion flow that disrupt the coherent pulsations, but which at least keeps the intermediate mass black hole interpretation viable and distinguishes M82X1 from the growing class of confirmed neutron star ultraluminous X-ray sources. And a comparison between theoretical models of disk precession including detailed general relativistic calculations of the length-stirring torques and the observed properties of the 62-day modulation which shows good agreement for black hole masses in the 400 to 800 solar mass range and black hole spin parameters above approximately 0.5 relative to the maximum possible value, and the spectral modeling employing increasingly sophisticated disk models that account for non-local thermalization, Comptonization, and general relativistic effects showing consistency with accretion onto an intermediate mass black hole at approximately 20 to 40% of the Eddington rate. And the broader consistency with theoretical expectations for hierarchical black hole formation in superstar clusters where numerical simulations predict that intermediate mass black holes in the several hundred solar mass range should form with reasonable efficiency in clusters with properties similar to the M82X1 host cluster. And collectively these multiple independent lines of evidence have built a strong case that M82X1 likely does contain an intermediate mass black hole with mass estimates converging around 400 to 800 solar masses though with substantial remaining uncertainties of at least a factor of 2. Though definitive proof remains elusive and will likely require future observations with improved capabilities including higher spectral resolution to better constrain the disk parameters and black hole mass through more detailed modeling of the thermal disk component, or longer-term monitoring to track the evolution of the quasi-periodic oscillation over many cycles and look for predicted changes in the period or for additional periodicities that might reveal orbital motion of a companion star or other characteristic timescales associated with the system geometry. Or direct imaging of the source environment at optical or infrared wavelengths with sufficient spatial and spectral resolution to identify a companion star if one exists and to constrain its properties through spectroscopy including temperature, luminosity, surface gravity, and chemical composition which would reveal whether it is a massive main sequence star or a more evolved giant or Wolf-Rayet star, or gravitational wave detections of similar systems during merger events which would provide clean black hole mass measurements free from the ambiguities inherent in electromagnetic observations of accreting systems. The implications of confirming M82X1 1 as an intermediate mass black hole extend to numerous areas of astrophysics beyond the immediate question of whether these objects exist, touching on fundamental questions about black hole formation and growth, about the physics of accretion under extreme conditions approaching or exceeding the Eddington limit, about the role of dynamics and mergers in dense stellar systems, about the origins of supermassive black holes in the early universe, and about the gravitational wave sources that will dominate future detection campaigns as the sensitivity of gravitational wave observatories continues to improve through planned upgrades to the LIGO and Virgo detectors and through the development of next-generation facilities including the Einstein telescope proposed for Europe and Cosmic Explorer proposed for the United States, and the answer to whether intermediate mass black holes populate star clusters in significant numbers affects predictions for gravitational wave detection rates since dynamical interactions in clusters produce black hole mergers at rates that scale with the cluster density and the black hole population, with estimates suggesting that clusters like the M82X, one host system might produce one intermediate mass black hole merger every several million years, and extrapolating to the full population of superstar clusters in starburst galaxies throughout the observable universe yields predicted detection rates potentially reaching several to tens of events per year for future gravitational wave detectors, and the existence of intermediate mass black holes in the present-day universe provides constraints on their formation efficiency and thereby on models of early black hole growth and supermassive black hole seeding. Since if intermediate mass black holes form readily in superstar clusters through either runaway collisions or hierarchical mergers, then similar formation mechanisms likely operated more efficiently in the early universe where gas fractions were higher and star clusters were potentially denser, and could have produced intermediate mass seeds that then grew through accretion and mergers to form the billion solar mass black holes observed in quasars at redshift 6 to 7, whereas if intermediate mass black holes prove extremely rare despite extensive searches, then alternative seeding mechanisms must be invoked, and the accretion physics revealed through detailed study of M82X, 1 informs our understanding of how black holes grow more generally. Since the transition from sub-Eddington to super-Eddington accretion regimes and the role of radiation pressure in shaping the accretion flow geometry remain active research areas with implications for understanding rapid black hole growth in the early universe where Eddington-limited growth may have been insufficient to produce the most massive high-redshift quasars within the available time, and the techniques developed for analyzing ultraluminous X-ray sources through combined spectral and timing analysis have broader applications throughout X-ray astronomy, including studies of galactic black hole binaries, active galactic nuclei, and tidal disruption events where stars are torn apart by tidal forces from supermassive black holes. And the recognition that careful multi-wavelength characterization and patience in accumulating long-term monitoring data spanning years to decades are essential for robust classification of exotic sources has influenced observing strategies across the field, encouraging systematic programs that track sources over extended periods rather than relying on single-epoch snapshots that can miss crucial variability or long-period modulations that carry essential diagnostic information.